Okay, so here is your review guide. The questions are in black, the new answers that I've just added are in red. So I defined heat and temperature and specific heat, what a calorie is, what a little c calorie is, and what a joule is. And then I gave you the conversions between a large C food calorie and little chemistry calories, and between little chemistry calories and joules. So joules are the smallest of all. And then collision theory asks what two key principles is collision theory based on? That's sufficient energy and correct orientation. So the sufficient energy comes from the activation energy of any given reaction. It's the energy going from reactants to the activated complex, which we'll go into more detail on in the next slide. So that's the sufficient energy portion. And the correct orientation looks like this. Two molecules come in a very specific way in order to hit with just the right orientation where the two black components are touching and the two red components are touching, therefore creating your red products and your black products. Incorrect orientation would not result in a reaction, and you would just end up with these same products, or these same reactants. So that one is correct orientation. Sufficient energy is the activation energy of any reaction. What does the raising temperature do to kinetic energy? It increases kinetic energy because kinetic energy is just the speed of the molecules, and temperature is just a measure of the speed of the molecules. Alright, next up we are going to draw and label an energy diagram. Alright, and so with our reaction diagram, you'll have a reaction drawn for you, and you'll have to label it. So let's label all the things you'll need to label on your reaction diagram. So I might say that here are the reactants and here are the products. Just like a chemical reaction, reactants are always on the left, products are always on the right. The same is true for here. Up top here is the activated complex. Now the activated complex is this molecule right here. It's not a product, it's not a reactant, it's an intermediate molecule. So that is our activated complex. Okay, now we're just going to give ourselves units in kilojoules so that we can show our delta E, our EA prime, delta E, EA, EA prime. Okay, so delta E. This is the energy level of the reactants, this dotted line just continued out here. So it's the difference between the energy level of the reactants and the energy level of the products. That's our change in energy. Our energy started at 20 kilojoules and went up to 30 kilojoules. So our delta E equals 10 kilojoules. Now our EA is our activation energy, and I'll write that up here. EA equals activation energy. Our activation energy is the energy it takes to go from the reactants to the activated complex. Activation energy gets you to activated complex. Our activation energy goes from 20 to 50, so our activation energy is 30 kilojoules. Our EA prime is the reverse activation energy. If we were to start with the products and this was a reversible reaction, it's the energy it takes to go from the products to the activated complex again. And that goes from 30 to 50, so our EA prime is our reverse activation energy, and that reverse activation energy is 20 kilojoules. This particular reaction, we have to put energy into it. We start with 20 and we end with 30. So we had to put 10 kilojoules of energy into it. If we had to put energy endo it, it is endothermic. This is an endothermic graph. We've got one more slide. Oh, so here we are. My diagram is endothermic because we had to put energy into it. We're going to draw an exothermic graph on the next slide. So draw the opposite graph as the one we drew on the previous page. So, with an exothermic graph, we have a high energy in the reactants and we have a lower energy in the products. So again, we'll say here's 10, 20, 30, we'll say that's right at 40 kilojoules, 50, 60 to make it quick. So it looks like our products are at 20 kilojoules and our reactants are at 40. So this right here is my delta E, and that delta E looks like negative 20 kilojoules. If your delta E is ever negative, that means that it's an exothermic reaction. You could also say, if you don't want to talk about negatives, that 20 kilojoules of energy was released. And then you don't have to call it a negative, you can just say that 20 joules of energy was released. Alright, that's the study guide. Good luck studying. Come in early if you have any questions.